Hi, this is a follow-up to our last class where we started talking about the scale example and we formulated our hypotheses, but I'm just going to go through the rest of the example in this video. So remember, we have 20 measurements, so differences between what we get for a measurement and the real weight of these objects, 10 grams. And the question is the scale biased? And we said that translated into a couple of hypotheses. Our HO, our null hypothesis, is going to be that the mu y's are equal to 0. So on average, there's not going to be a difference between the measurements and what their true weight is. And then HA is that there is bias. So note that there's not a direction built into this, so it's going to be not equal to for our HA. Because if it's greater than 0 or less than 0, we're going to have some bias. Okay, so what we could do next then is, that's step 1, formulate your hypothesis. Step 2 is figure out what your test statistic is. So here we think we're going to be using a t-test. We used a t-confidence interval. So for this, our observed test statistic would be the sample mean, and that's an x, but it should be a y, because we're dealing with y's here, minus the hypothesized value for the true mean of the y's, which is going to be 0, divided by the standard deviation of my y's in the sample, divided by the square root of my sample size that I have. So that's going to be 0.175, subtract 0, divide it by, and then my standard deviation is this 19.43275, divided by square root of 20. So that's all on my denominator. When I work that out, I get 4.027. So there were a couple of conditions that we said we needed in order to know which distribution this test statistic came from. First of all, we need to know that we have a SRS or something that can be treated as an SRS. Second of all, we need to know that the y's are normal in the population. So both of these we talked about in class when we were looking at the confidence interval example. We were told that these measurements were done at randomly selected times, so that's probably fine. And then the y's being normal, what we did is we looked at a QQ plot of our sample, and it didn't look too bad. So the points all seem to be close to a straight line. With some, we saw some weird stuff with rounding, but it didn't look too non-normal. So I guess we're okay to proceed and say that this t-obs, this 4.027, probably came from a t-distribution. All right, so there's two ways we can proceed from here. We can use the critical value method, or the rejection region method. Or we can use the p-value method. So I'll start with this one. I want you guys to understand how they both work. So with the rejection region method, what we do is we need an alpha, and I didn't give you an alpha on the previous slide, so I'll give you one here. Let's just use alpha of 0.05. That's a commonly used one. And what we're going to do now is we're going to draw a picture of the t-distribution that we're going to be dealing with, which is t with degrees of freedom equal to n-1, which is 19. It's going to be centered at 0. They all are. And I don't want to use my test statistic in this method yet. What I want to do is I want to take this alpha, and remember my HA was that mu y was different from 0. So it's a two-tailed test, which means that I need to think about both tails when I work through this. So what I want to do is take my alpha. I want to put half of it up here and half of it down here. to find the t critical values that I need. So this guy's going to be t alpha over 2, and this guy's going to be minus t alpha over 2. And my alpha was 0.05 here, so that means that this guy is t 0.025, and this is minus t 0.025. All right, so we can look these up in the table. We know we're restricted to the degrees of freedom 19 row, so we're here. So we look across and we want to find the number that goes with a tail area of 0.025. Looks like that one. So that tells me that this guy is 2.093. And it tells me that this guy is just the negative version of that. So the rejection region method says that if we get a test statistic anywhere above this or below this, we reject the null hypothesis. So we go back to our test statistic. What was it? It was 4.027. 4.027. So our test statistic is out here somewhere. T obs is there. So we reject our null hypothesis. Okay, so that's one way to do it. The other way is using p-values. So we can draw our picture of the t-distribution again. But now instead of using the distribution to put numbers on here, what we're going to do is we're going to use our test statistic. We're going to use our test statistic. So my t-obs, I'll make my line go out further here. My t-obs is probably out here somewhere. So to get the p-value, what I want to do is I want to find the probability of observing results at least as extreme as I did under the assumption that the null hypothesis is true. So the null hypothesis being true is what let me draw this picture in the first place. It said that my standardized y bars centered at 0 followed a t-distribution. So if mu is really 0 here, then this distribution will be okay. So if it's not, though, my number is actually going to come from a different distribution, one that's slid along this axis a little bit. So I mean, you could imagine that if I have my t-obs way out there, it might have come from a distribution that looks something like this. Might have been more likely to come from a distribution like that. Anyway, that's not my p-value. So my p-value here is that area, but since I have a two-sided alternative hypothesis, you need to also look at the negative side of that. And take that area as well. Yeah, so we have our t-obs from the calculation we did on the last slide, 4027, so this would be minus that. From the tables, what do we have? We're still dealing with the 19 row. What you want to do is you want to go along the 19 row, your degrees of freedom row, and find the closest value of the t random variable you can to your value. So if I go across here, it looks like as close as I can get is this one here. Then my values stop. That tells me that there is a 0.0005 probability of observing a t-value, so t random variable value, that's at least 3.883. So that tells me that, and maybe I'll switch colors again. Table tells me that that tail area is 0.0005, where that guy is 3.883. So what I can conclude based on the table is that the probability that t is bigger than my t-obs, so 4.027, is going to be something less than 0.0005. But that is not my p-value. My p-value is actually going to be that plus the other side. And since the t-distribution is symmetric around 0, the p-value is just going to be 2 times the one tail. Is equal to my p-value. So we can say that my p-value is going to be something less than 2 times this thing. But that's all I can say. That's all I can say based on my table. 001. Yeah. But we can use R. We could use R to get an exact p-value here. And I did. Here it is. The p-value for this test is that. So the code for a t-test in R is just t-test, so that's nice. It's nice and intuitive. And then it gives you lots of information. It even gives you a 95% confidence interval for mu, which is the same one as we got before. It gives you your test statistics. So here's our t-obs. It gives you your degrees of freedom, and it gives you the p-value. So here, since it's a two-sided alternative, the p-value is equal to the probability that t, the absolute value of t, is greater than or equal to t-obs, the absolute value of that. Yeah, what else is here? So yeah, this is a 95% confidence interval for mu y. So since we said that, we have to set our significance level at the beginning too, before we see our data. Since we set it at 5%, then we compare that to our p-value and we decide, hey, our results look even more unusual than the cutoff that we set, which is our significance level in advance for what we consider to be unusual. So we're going to reject the null hypothesis since our p-value, which is less than 0.001, or here we have the exact number, is less than alpha equal to that. So we're rejecting the null hypothesis because our p-value is smaller than alpha. So a question, and feel free to pause the video and think about this for a little bit on your own first. What does that p-value of 0.0007198 actually mean? So of these, which is the best interpretation? So pause it and think about it. Yeah, so think about what a p-value is measuring. It's the probability of observing results at least as extreme as the results that you observed under the assumption that your null hypothesis is true. So if we look at these on average measured weights on the scale tended to differ considerably from actual weights, assuming the scale is biased. So this doesn't look right, assuming the scale is biased, because that's like us saying assuming HA is true. Tests aren't set up that way. They're set up assuming HO is true. So that's no. B, measured weights on the scale differ from actual weights on average. So this is just saying HA. So does that p-value mean HA is true? No, it's not set up to tell us that. It's only set up to give us evidence, tell us how much evidence we have against HO. C, there's no difference between the measured weights on the scale and the actual weights on average. So that's just kind of rephrasing what HO is. Again, test is not set up to tell us if that's true or not. Hopefully D works. On average, measured weights on the scale tended to differ considerably from actual weights, assuming the scale is not biased. Okay, this is looking promising because we're assuming HO. And measured weights on the scale tended to differ considerably from actual weights. So considerably, yeah, doesn't mean that it had to be a huge difference. It just means that it's more different than we'd expect to see if it was just due to chance. So basically, our test statistic ended up way out in the tail, further out in the tail than we thought it should be if the results were just due to chance. So yes, this is the closest to what a p-value means out of these options. Let's think about this some more because it's an important idea. Our rule is that we reject the null hypothesis if the p-value is less than or equal to the significance level that we set out in advance. So that significance level is like our cutoff for what we're going to see as unusual. So it basically tells us how far do you have to go away from 0 in this t-distribution in order for us to say that the results are unusual. Small p-value implies there's a small chance that we'd observe a test statistic value as far away from the null value under the assumption that HO are really true. Now, there's two ways that could happen. Maybe HO really is true and we just observed an unusual value. That's not impossible. Even if we're way out in the tail, it's going to happen sometimes, right? And then the second way it can happen is if HO is not true. So maybe the distribution, maybe the mean was different, maybe it was actually higher, so the sample wasn't taken from the distribution I'm assuming that it was taken from. The smaller our p-value gets, the more we side with 2. Now, just like confidence intervals, we can't see what's going on. We can't see the actual truth. So what we're doing with the hypothesis test is we're trying to make a decision about whether or not we should reject the null hypothesis based on the information we can see in our sample, but that doesn't represent the truth necessarily. So errors are going to be a natural part of hypothesis testing. The two kinds of errors, they don't really have informative names, unfortunately. Type 1 error is that we reject the null hypothesis when we shouldn't, so when it's true. And the probability for that, so the probability of type 1 error, is something that's familiar. It's just alpha. So we control how small that is by setting our significance level. So even if we set it super low, we're still going to reject, we're still going to reject the null hypothesis when the null hypothesis is in fact true, sometimes. The other side, type 2 error, not rejecting HO when HO is false, so not rejecting HO when we should. Here, the probability of type 2 error is called beta. Another related concept that you've seen before is power, and that's the probability of rejecting a false HO. So it's 1 minus beta. And power and beta are both functions of what the parameter really is. So they vary depending on how far mu, say in our situation, is from the null value of mu. And you can calculate them, and the book actually goes into calculating calculating them. I'm not going to ask you that on the final, but I encourage you to read it just so that you understand that, yes, they're functions of the true parameter values, and yes, we could calculate them if we wanted to, but I won't ask you on the final. I do want you to be able to distinguish between these two types of error, though, and understand that alpha, probability of type 1 error, and beta is probability of type 2 error. I do have one extra example about these errors. So pause it and think about it. Pause it and think about it. All right, so I'll go through it. A computerized medical diagnostic program scans the results of routine blood tests and either clears the patient, that means decides the patient's healthy, or refers the case to a physician for further testing and follow-up. Suppose this program misses somebody who really should be referred to a doctor for further testing. What type of error has been made? So in this, you have to kind of think, all right, well, what's HO and what's HA? We have this assumption about a reality, and then we have what the hypothesis test concludes. So an assumption about reality, HO is healthy. Remember, HO is kind of the null value, the value or the situation where there's no action involved. You're going to assume this until the data suggest otherwise. So that's why we pick it to be the healthy one. And then HA is the non-healthy one. So if the data suggests, so if the test results suggest that she's not healthy, then there's going to be further action taken. So it's an actionable outcome. Then we can either reject HO or not reject HO in both of these situations. And the question was asking, if the program misses somebody who really should be referred to a doctor for further testing, what type of error has been made? So the test misses somebody who should have been referred to for further follow-up. So we're on this situation, not healthy, and okay test result. So it's not rejecting the null hypothesis when we should. That sounds like a type 2 error to me, and it is. So all of these four situations, sometimes we end up at the right spot with our happy faces here. Sometimes we've made an error. And of course, just like for confidence intervals, we don't know what we did unless we're running a simulation. We just don't know if HO or HA is really true. So it's unknown probability of 0 or 1. It's true, false, logical. And on these branches, we have these other probabilities. So the probability of type 1 error is our alpha, and then the probability of not rejecting HO when HO is true is 1 minus alpha. And there is our beta and our power. Again, though, I said I'm not going to expect you to calculate those things from scratch, but I do want you to understand what they are, what they're quantifying, and understand that power and beta are functions of the parameter value. Okay, so that brings us to the end of chapter 9. I went through this example in a lot of detail just so that you guys would all have it. The book goes into a lot of detail, like I said, for the power and beta and some other things in those first few sections, but this list kind of tells you what I see as the important things, and I'm telling you to skip section 9.5. Okay. All the best with your studying, everybody. Good luck.